Problem number 8 next. Here we have the function f from the Cartesian product a times b into the Cartesian product b times a, and f is defined like this: f of a comma b is equal to b comma a. So the function f flips the coordinates, and a and b of course are some sets. We have to prove that this function is a bijective function. It's a 1 on 2 function. So here the solution pretty straightforward. So we take two elements in the Cartesian product a times b, and they are a1 comma b1 and a2 comma b2. To consider them, we would need these coordinates, so we start like this. Let a1 and a2 be two elements in a, and b1 and b2 be two elements in b, such that the f images of these ordered pairs are equal. Now to prove that f is 1, we have to prove that the ordered pairs themselves are equal. Now by definition, well, we don't have that here, but by the definition of f, we can go back and see the question. This is equal to this, b1 comma a1. Like that, this is equal to b2 comma a2. Now we know that when two ordered pairs are equal, their corresponding coordinates are equal. So this implies b1 is equal to b2 and a1 is equal to a2. But when that happens, a1 comma b1 is also equal to a2 comma b2, because a1 and a2 are the same and b1 and b2 are the same. So that's it. We have shown that when outputs are equal, inputs are also equal. So that means f is 1. And next we go for ontoness. For ontoness, we take an arbitrary element in the codomain of f, which is b times a, and that element is say b comma a. Then obviously b belongs to b and the second coordinate a belongs to a. But then the ordered pair a comma b will belong to a times b. And not just that, if you calculate its f image, by definition that is b comma a. So your arbitrarily chosen element in the codomain appears as the image of some element in the domain under the function f. So by definition f is onto, and being 1 and onto, f is a bijective function. So you write the last line. Next we have number 9. Here you see a function from the set of natural numbers into itself, and the rule defining f is this. When your input n is an odd natural number, for example 1, 3, 5 like that, then the output is n plus 1 divided by 2. Whereas if the input is even, then the output is 1/2 of it. Let us take a moment to see that this makes sense. If your n is odd, n plus 1 is even, and because n is a positive integer, n plus 1 is also a positive integer. So when you divide a positive even integer by 2, you get again a positive integer. So this output really belongs to n. But if your input n itself is a positive integer, again dividing that itself by 2, you again get a positive integer. So yes, this function makes sense. Now we have to state whether the function is a bijective function, and we have to give justification for our answers. It's not that we just simply write it is bijective or not bijective and that's it. And the solution is quite easy and short because it is not bijective. You notice this, f of 1, because 1 is an odd integer, so this part of the definition has to be used. 1 plus 1 divided by 2, which is 1. But that is also equal to 2 divided by 2, which is f of 2. f of 2, because 2 is even, will be equal to 2 divided by 2 according to this part of the definition. So the f images of 1 and 2 are both equal, although 1 and 2 are distinct. So how can it be 1, 1? It's 2 to 1. So that is why it's not 1, 1. And being not 1, 1, obviously it cannot be bijective, because a bijection is 1, 1 as well as onto. So you see that you need not even check whether the function is onto or not. It may be either, but it's not bijective, and that's it. There the solution ends. Next we have 10. Here, first of all, we consider these two sets A and B. A is the set of all real numbers from which 3 has been removed. That means A consists of all the real numbers except 3, and B is the set of all real numbers except 1. And then we consider this function f from A to B. And the rule defining f is this: x minus 2 divided by x minus 3. You can see why we are removing 3 from R and why that is the domain of this function. Had 3 been present here, this would be meaningless when x is equal to 3, because then you are dividing by 0, which is not permitted. That is why 3 has been removed. So obviously there is nothing wrong with this function. For every x in A, this is a legitimate real number. It's a different matter whether that real number belongs to B or not. Okay, actually it belongs to B, but that's not what we have to check. It is given that it's a function, so that means you can be sure that for any x coming from A, this x minus 2 divided by x minus 3 really belongs to B. That means it's never equal to 1. It's actually very easy to check, but that's not our aim. Our aim is to decide whether f is 1, 1 and onto with justification. The truth is that the function actually is 1, 1 and onto. It's a bijection. So we first go for 1, 1-ness. We take any two elements x and y in the domain A such that their f images are equal, and those f images are this: x minus 2 divided by x minus 3 and y minus 2 over y minus 3. And then we do cross multiplication. So we get x minus 2 times y minus 3 equals y minus 2 times x minus 3. And then what happens? We do the multiplication. Xy minus 3x minus 2y plus 6, that is equal to yx, that also I have written as xy, minus 3y minus 2x plus 6. So xy and 6 cancel out from both sides, leaving us with this: minus 3x minus 2y equals minus 3y minus 2x, which you can see, if you change sides, you can write things like this: 3y minus 2y is equal to 3x minus 2x, or y is equal to x, that is x and y are the same. So if outputs are equal, then so are the inputs. So that means yes, f is 1, 1. And next we show that f is also onto. For onto-ness, we start by taking any point z in B. If you want to call it z, you can. Some people call it z. Now what is B? Let us recall what the set B is. B is the set of all real numbers from which 1 has been removed. So that means our set is not equal to 1. And because it's not 1, we can consider this real number: 3z minus 2 divided by z minus 1. You may wonder why this real number suddenly. We are coming to that afterwards. Okay, but let us first see something else. What will happen if this is equal to 3? Then you have 3z minus 2 equal to, if you multiply both sides by z minus 1, 3 times z minus 1, or 3z minus 3. Now cancelling 3z from both sides, you get minus 2 equal to minus 3, which of course is not possible. And that is why our supposition is wrong. That means this cannot be equal to 3. And what does that tell us? It tells us that this real number is in the set capital A. And as such, we can calculate the f value of this real number. So our number 3z minus 2 divided by z minus 1 belongs to A, because it's not equal to 3. And A is the domain of our function f. So we calculate the f value of this. F by definition is input minus 2 divided by input minus 3. Alright. And then if you go through the manipulation, I could have written this divided by z minus 1 and this divided by z minus 1, but ultimately those two z minus 1's cancel out. So I have simply written the numerators here, and they are 3z minus 2 minus 2 times z minus 1 or minus 2z plus 2. Similarly, here 3z minus 2 minus 3 times z minus 1, that is minus 3z plus 3. Now you can see that minus 2 and plus 2 cancel out and 3z minus 2z is z. So that is the numerator, and the denominator is these 2 cancel out and 3 minus 2 is 1. So that means we are getting z. What does this tell us? It tells us that for our arbitrary choice of element in the codomain, there exists an element in the domain whose f image is equal to this. So that tells us that f is onto. Hence f is onto, and we have shown that the function f is both 1, 1 and onto. But the question remains, how did I figure this out? That for a given z, this should be my pre-image. That justification is given here. This is a rough work. You can do it alongside the problem by drawing a vertical bar and then doing the rough work on that side. You already know. So what is it that we need? We started by taking any element z in the codomain B, and we are searching for an element x in A such that f of x is equal to z. So that means z is equal to this. This is f of x, x minus 2 divided by x minus 3. And then what do? Because we are searching for x, we solve for x in terms of z. So we do the multiplication, z times x minus 3 equals x minus 2. That means zx minus 3z equals x minus 2. And then we are trying to solve for x, so we bring all the terms having x to one side. So that way we get zx minus x equal to 3z minus 2, or z minus 1 times x equals 3z minus 2. And then we divide both sides by z minus 1, which we can because z is not equal to 1. So that fact is used here, and you get just this. But then only this is not enough. You have to also show that this number really belongs to A, and that is why we did those things in the beginning. We supposed that this is 3, and then we arrived at a contradiction showing that it cannot be 3, and that told us that yes, it actually belongs to A and it qualifies to be a pre-image for our z under F. And then we proceeded and completed the solution. Next, in this 11th one, it's a multiple choice question. A function is given from the set of real numbers into itself, and the definition is this: f of x equals the fourth power of x, and these are the options. F is 1, 1 and onto, that means f is a bijection, or f is many 1 and onto. F is not 1, 1 but f is onto. Option C, f is 1, 1 but not onto, and option D, f is neither 1, 1 nor onto. I am not writing it as a formal solution. You can write the steps, you can give these justifications. You can write your own sentences. That's what I am saying. F is not 1, 1 because just like the squared function, the fourth power, that function also maps all the real numbers onto non-negative real numbers. Even when the input is negative, the output is positive. So we use that with -1 and 1. So both the outputs of -1 as well as 1 are equal to 1 because the fourth power takes care of the minus and makes it plus. So that is why different inputs are giving us the same output. So it's not 1, 1, it's 2 to 1. So that means f is not 1, 1. And again, that same fact, all the outputs are non-negative, but the codomain has negative numbers also. In particular, there is -1, which thus does not appear as the output for any input under f. So how can f be onto? So f is neither 1 1 nor onto. So this is the correct option. And finally we have number 12, which is similar, but the function is different. Again f maps r into r, but this time f of x is equal to 3x, and the same options, exact same options. In this case the function is a bijection, it's both 1 1 as well as onto, and that is pretty easy to see. You just go for the verification. The steps are available here. You start as you always start. You take any 2 points x and y in the domain for which the f values are equal. So with this f now, that means 3x is equal to 3y, and then you cancel 3 from both sides, obtaining x equal to y. So that gives you 1 1ness. And then you take any point set in the codomain and guess what your pre-image should be. It's not as difficult as that one. You just want a real number, so that if you take 3 times the real number, you should get z. So obviously that real number has to be z divided by 3, which is available in the domain. So that way you get ontoness also. So that means in this case option A is the correct option. F is the bijection. And with this set of exercises itself ends. After this also there is one section where we have composition of functions that we will start next week. So see you next week with that. Until then, this is me, Lucifer, from A Mathematical Room. Have a nice day.